Hi everyone, this is Dr. Sporsky, and this is going to be the slides for Chapter 11 on visual information. And I just want to give you guys a heads up that this is going to be the format that I use for the remaining lectures for the semester. So I will be recording all of the slides. And I know this is going to be a little bit different than having a face-to-face lecture, but this is the best thing I could come up with. I thought it would work the best. And I know that YouTube videos are simple to use for you guys too. So hopefully this is a easy way to get the information and learn it. Of course, going along the way, if you have any questions about anything in the materials, please feel free to send me an email and ask a question, and we'll go from there. Um, some other things as well, I feel like, just because you're not getting that face-to-face lecture you got when Dr. Starling was present, I would suggest that after listening to my lecture, you make sure that you're reading the textbook and everything like that as well, just to make sure you have a good grasp of the material. Um, and lastly, as we go through the slides, I'm going to be making comments throughout if I feel like there's something that I want you guys to do discussion board on. I know you also have the ZAPS, and the ZAPS are indicated throughout these slides of where you should be completing them. So as far as that's concerned, I know that if you see that there's a ZAP and you complete it, that you're paying attention to the lecture. But also, I want to add some discussion boards in here as well that I'm going to say, hey, this is something that I want you to um, put into the discussion board, and I will indicate where to find it and everything like that. And this gives me the information that you guys are watching my videos and listening for the discussion board comments and actually participating in the class for the rest of the semester. Because we have no face-to-face participation except for the presentations at the end of the semester. So with that being said, let's get started. I took out Dr. Starling's on the docket slide just because I felt like it didn't really make sense for me to go over that. So we're just going to jump right into visual imagery. Okay. So, visual imagery occurs when we have thoughts that involve pictures. Sometimes it seems like we're thinking in pictures, but honestly, that's almost impossible because we don't really have an eye in our mind. The information in this section of slides is going to mainly target our visual knowledge and visual thoughts and try to distinguish what's going on in specific situations. So to start out as an experiment, I want you to imagine your dorm room or your bedroom, and I want you to think about how many drawers are in your dresser. So once you have a good picture of that, I now want you to imagine walking from your room to the main entrance of your building. It's almost like what we call a cognitive map, where you're trying to figure out how to get from point A to point B. And just notice that it might be a little difficult to think about things like different things like windows and stuff like that. Even if I said, hey, think about what your home is like when you're not at school. Think about how many windows your house has. You might notice that you feel like you have to actually use your hand to count those windows and think about it a little bit. Um, so now, as another little experiment, I want you to visualize someone close to you, like your mom or your dad, or you can even visualize someone you see in the media, like a celebrity. I want you to try to think about all their major features, what their hair looks like, their eye color, what they were wearing the last time you saw them, specific characteristics that fit for that person and no one else. So when you do these things, thinking about your house, thinking about your dorm room, thinking about a person, mental images are often invoked when we think of information like this. We actually picture that in our mind. You might also have this when you're doing things like reading a book that you enjoy, or maybe even you might daydream sometimes and have mental images that pop into your head from those daydreams. Sometimes these visual images are very important for us because they can aid us in things like decision making. Um, for example, like if you're out shopping, you might be looking at a particular shirt and think, well, will this look good with my polka dot pants? Um, because, but because we have no true eye, what are these images? Um, we feel like we're looking at pictures, but there's no eye in the mind. What is actually the nature of the mental image? So that's some of the stuff that we're going to talk about a little bit in these set of slides. Okay, so I want you guys to think of a mental image about something. It can be whatever you'd like it to be. And I want you to try to think about whether or not that image in your mind is more like a picture or a verbal description. So just to give you some definitions, if it's a picture, it's the visual features that are prominent. That when you describe it to somebody, you're going to talk about the things that you visually see. When it's a description, it's that the verbal features are prominent. So it's more like how you describe things more than how you see them, if that makes sense. Um, so to give you a little bit more information about that, we're going to talk a little bit about a study involving depiction versus description. Okay, so what I want you guys to do next is I want you to form the mental images of a cat, and I want you to think about what distinctive features of a cat you would mention if you were to write a paragraph describing a cat. You'd probably think about things like their whiskers, their claws. You wouldn't probably include the fact that a cat has a head, um, because that's just obvious. You know that cats would have heads. It wouldn't be worth mentioning. You would be more likely to describe the different things that make a cat a cat. Um, so now, in contrast, I want you to think about what if I asked you to draw a picture of a cat. So in this format, the cat's head would be prominent for the reason that you generally, a big part of a cat is what its head looks like. Um, so the claws and whiskers might be something that are less important. They're smaller features. You might not include them in your drawing. But if you were describing a cat, you would be much more likely to describe the things that a cat has that makes it a cat. Whereas when you're drawing, you'd be much more likely to draw things that you wouldn't mention in that description. And I hope that makes sense. So, the point here is that there's a pattern of what information is included depending on whether or not you're visualizing something and depicting something versus whether you're describing something. So in a particular study by Coslin in 1976, research participants were actually asked to form a series of mental images and answer yes or no questions about each of them. For example, they were asked to form a mental image of a cat and then were asked questions like, does the cat have a head? Does the cat have claws? Participants responded to these questions quickly, but were quicker to respond to things involving to the head question than things like the claws question. So this difference suggests that information quickly available in images follows the rules for pictures, not paragraphs. So you're more likely to mention things based upon what you would see in an image than what you would describe in a paragraph about something verbally. In a comparison group, though, another group of participants, they were asked to merely think about cats, and they were given no mention of a picture of a cat or thinking of what a cat would look at. Like these participants, when they were asked the same questions, gave quicker responses about things like claws or whiskers than about the fact that the cat had a head. So it's the exact opposite of the first group, which was asked to form a mental image from the ones that were asked to answer questions. So it seems that if people have the option of thinking about cats via a mental image or the option of thinking about cats without imagery, that changes the way that we come up with the information, whether we describe it or depict it. In another experiment, participants were asked to memorize a fictional map, which you see in this picture. And so they were asked to memorize the map and the landmarks that were on the map, like the straw hut and the tree and the well and so on. Experimenters made sure participants had the map memorized and asked them to draw a replica of it from memory. And once they could do this, the experiment began. So participants were asked from that point to form an image of the island and to point their mind's eye at specific landmarks. So for this experiment, we'll pick the well. And then they would pick another landmark that was mentioned, and they were asked to imagine a black speck moving in a straight line from the first landmark to the second. When the speck reached the target, participants pressed a button, stopping a clock. So what this was looking at was trying to provide a measure of how long the participants needed to scan the map and figure out the distance that they would think would be from the well to the hut. The same was done for the well and the tree and the hut and the patch of grass. And so basically the researchers were getting a lot of data about the scanning that occurs. So what they found was that the amount of time it took to scan relied on the amount of distance that the objects were from each other on the map. So it took much quicker for individuals to scan in their heads the distance from the well to the tree versus, for example, the well to the patch of grass. So here is the graph that involves image scanning. So images were scanned at a constant rate. Sorry, and doubled the distance. There was double distance equal to double time to respond. So the longer it took to scan, the longer it took to respond. And physical properties of the map were preserved in the mental image. So you could see that based on response, the people took longer, for example, for the well to the grass. So there is a mental scanning ZAPS that you are to complete in this section of the slides. If you want to pause here and go ahead and go do that, that's fine. If you want to do it later, it's up to you. I'm not going to really discuss it so much right now, just because it's difficult for me to go and do anything with the ZAP while I'm recording. Okay. In a study that looked at whether zooming affects how long it takes us to scan mental images, we saw that there were similar results. So if participants were given a task that requires a zoom in their imaging, so for example, looking at a small detail, like if wondering if a mouse has whiskers next to an elephant, we do see that there's about the same response time as it would take to zoom in real life as it does with the mental image. So we also see that this depends upon the task. So zooming in on a mouse having whiskers next to an elephant takes longer than zooming in on a mouse having whiskers next to a paperclip because they're similar in size. In another set of experiments, sorry, I got stuck for a second looking at something involving this task. In another set of experiments that were looking at mental rotation by Shepard, Cooper, and Metzler, participants were asked to decide whether the displays that they were shown of different shapes, as you can see on this page, on the slide, were the same shapes or two different shapes, so if it was the same shapes just shown from different perspectives. So basically, in other words, when somebody is looking at a particular shape, are they able to rotate it in their mind and be able to look at it from different perspectives that they would see visually? Or is this too difficult for our brain to do? Because when you have something in front of you, it's really easy to rotate it and look at it when you're holding it in your hand, but does our brain have the capability to do this on its own? I know, and I've also taken exams and things like that have these types of questions on them, and they always really frustrate me, like on geometry exams and things. So I don't know if anybody's ever experienced this, but anyway, so in these studies by Shepard, Cooper, and Metzler, they were looking at if it was possible to rotate the form that was shown to them, so that it would look like other forms that were shown to them. So to perform a mental rotation task, participants seem to first imagine one of the forms rotating into alignment with the other. So they actually imagine it shifting so it matches the alignment of the other form. Then once the forms are oriented in the same way, participants make their judgments. So this step of imagine rotation obviously takes some time. And it's interesting because it would take about the same amount of time as we would rotate in real life, but it takes more time depending on how much rotation would be needed of the figure to determine whether they are the exact same figure. So basically, the more rotation it would take in your mind is how long it would take to answer the question. So response times are clearly influenced by how far apart the two forms are in their initial orientations. So imagined movement resembles actual movement. So the further you have to imagine a form rotating, the longer the evaluation takes. So it would be, if you were imagining something versus doing it in real life, it would take about the same amount of time to rotate it in real life as it does to rotate it in your mind. I hope that all makes sense. So here's just a slide looking at the different data. And now you get to try it for yourself. There is a ZAPS on mental rotation. So you once again can go ahead and do that ZAPS now, or you can wait until later to do the ZAPS after you finish listening to this slide presentation. So if there's a little bit of choppiness between the last slide and this one, I apologize. I stuttered a little bit, so I wanted to re-record. So what can we conclude? Are mental images like pictures, or are they more like descriptions? So obviously, mental images provide quite a bit to help us represent the world, both visually and spatially. But we know that things like visualizing something, like we'll say visualizing a monkey, is quite different from thinking about the word monkey, which is different from contemplating what the idea of a monkey is, like what a monkey is like. As one key difference, images are like pictures in the fact that images show exactly what a form looks like to us. So visualizing a monkey will highlight what a monkey's appearance is in your thoughts and make it much more likely that you'll be reminded of other forms having similar appearances. Thinking about a monkey without thinking with an image won't highlight its appearance so much. It might highlight more like what a monkey's behavior is than what a monkey looks like. So along with this, trying to call an image to mind will also help your thoughts organize themselves, and so that you can figure out how to organize your ideas and organize the shape and flow of those ideas. However, mental images are not picture-like as well. So while they are in some ways, they are not in other ways. They are more organized in a way that pictures are not, and this organization can influence the way your thoughts are sequenced with your understanding of the image. So, basically, you might imagine different objects in a certain way and not imagine them in the way you would as if you would actually, or you might not think of them in the way you would as if you actually had that object in front of you. So obviously images have a lot in common with pictures, but they're also different. And your book talks about how the common phrase mental pictures is misleading, and it would be more accurate to say that images are picture-like as not actual pictures. So even though we answered our question a little bit, we're going to look at some more things to back whether or not mental images are pictures based on some more research and brain scans and things like that and imaging. So in a study looking at whether or not imagery and perception rely on the same system, there were some interesting things discovered. So Siegel and Fusella in 1970 and 1971 completed a study where participants were asked to detect faint signals, either something that was visual, a very dim visual signal, or let me go to that slide, or a soft tone. On each trial, the task was merely to indicate whether a signal had been presented or not. Participants did this in one of two conditions. They either were trying to form a visual image before their mind's eye, or while forming an auditory image before their mind's ear. So they were trying to either imagine visually the stimulus, or they were trying to auditorily imagine the stimulus. So you can see this two by two design, looking at the percentage of detections. It was noted that participants were less successful in detecting a weak visual signal if they were simultaneously maintaining a visual image than if they were maintaining an auditory image. So they were able to detect a visual signal better if they were not trying to maintain a visualization. The reverse was true with auditory signals. Participants were less successful in this detection of maintaining an auditory image than of visualizing. So basically, visual images often led to false alarms for participants trying to detect visual signals, whereas auditory images led to false alarms for auditory signals. So Siegel and Fusella their participants were trying to visualize one thing while perceiving something different. But there was another study where the question was, what happens if participants are contemplating a mental image related to the stimulus they're trying to perceive? Can visualizing a possible input pave the way for perception, or does it cause a problem? So Farah in 1985 had participants visualize a form, either the letter H or the letter T. Um, a moment later, either an H or a T was presented to them, but at a very low contrast, making it difficult to perceive and determine what it was. With the setup, perception was facilitated if participants had just been visualizing the target form, and the effect was quite specific. So visualizing an H made it easier to perceive an H, visualizing a T made it easier to perceive a T. So this provides more confirmation of the claim that visualizing and perceiving draw on similar brain systems and mechanisms, and that these activities actually prime each other. So they support each other and help you figure things out with each other activity. So what happens when we actually look at images and do some imaging studies on the brain during different types of tasks? So in a study by Coslin in 1993, there was PET imaging during two different types of tasks, a task when somebody was perceiving and a task when somebody was doing imaging. And what was discovered was that there is a large overlap in brain activity during these tasks. So this overlap in brain activity shows that similar systems are used in these different types of tasks, and that the brain is not using different areas to work on these different tasks. Also in a study in 1998 by Goebel and et al., we saw that when participants were asked to visualize particular movement patterns or imagine movement patterns, we saw that certain areas in the brain were highly sensitive to motion in ordinary visual perception, and it turns out that the same brain areas are activated when participants are just imagining movement. So once again, those two systems are interacting, that the systems are all interacting. Some other cool things about the parallels between imagery and perception have been documented in other studies. So we know that different areas of our occipital cortex are involved in different aspects of perception. Areas V1 and V2 in the cortex, for example, are involved in the earliest stages of visual perception, and they respond to low-level features of input. So what's really cool is that these same brain areas are very active whenever participants are maintaining highly detailed images, and that the amount of brain tissue showing activation actually increases as participants imagine larger and larger objects. So we see that the brain is sensitive to motion in visual perception, and also when we're imagining movement, the brain is sensitive to when we're visualizing something and seeing something in the same way it is as when we're imagining something. So the brain is active when we are doing both of these tasks regardless. So there's always a large overlap in brain activation. Another cool thing that looked at imaging of imaging, another study done by Coslin, who was apparently the imaging guru, that when he did transcranial magnetic stimulation over area V1 in the brain, which is the area in the brain that axons from the visual system first reach the occipital cortex, so where we first start perceiving visual stimuli, when there was disruption through TMS, during a perception task versus an imaging task, it was noted that obviously TMS caused problems with vision because you're disrupting the neurons in your brain from understanding the stimuli you're seeing. So obviously there are problems in vision, but it also caused parallel problems in visual imagery. So this is an argument that area V1 in the brain is important both for the processing of visual information and for the creation of visual information or visual images. So that's kind of just a cool study looking at how those two things are related. When we look at people that have brain damage or some sort of issue with their brain, we also find parallels between visual perception and visual imagery. So in one study, they looked at patients who had unilateral neglect. Remember that these patients ignore one side of space when they have unilateral neglect. Sorry. In one case, a patient suffered a stroke and he had this neglect syndrome. And if he was shown a picture, he seemed to see only the right side of it. If asked to read a word, he only saw the right half. This is a reminder from chapter 5. And the same pattern was evident in the patient's imagery. In one test, he was urged to visualize a familiar plaza in his city to list the buildings in view in the image. If the patient imagined himself standing at the northern edge of the plaza, he listed all the buildings on the plaza's western side to his right, but none on the eastern side on his left. If the patient imagined himself standing on the southern edge of the plaza, he listed all the sites on the plaza's eastern side, but none on the western side. So once again, he neglected half of the imagined scene, just as he did with scenes that he was actually perceiving or seeing in person. So I'm actually going to skip this slide on functional equivalence, but you can read about it in your text as seeing that there are other studies that show that as visual acuity decreases into the periphery, you have the same effect observed in imagery. So if something is right in front of you, in person, you're more likely to see it right in front of you, obviously in person. But if you're imagining something, you're more likely to see the details in that image that are the closest to you than the ones that are off to the side or in the periphery. So we don't visualize the periphery in the just like we have a harder time seeing things in the periphery in real life. Hope that makes sense. So whatever's in your peripheral vision in real life is harder for you to imagine things that are in your peripheral vision in your brain. So do imagery and perception rely on the same system? In some ways, yes. We see that many visual imagery tasks are in a line with the way when we're thinking things and actually seeing things, that a lot of the same systems are being used. So along with this, we have to remember that visual information, visual imagery is different than spatial imagery. So visual imagery represents how something looks, whereas spatial imagery represents movements or relationships. So for example, visual imagery would involve that map task. So in another study that's pretty interesting, we see that individuals who are blind from birth show the same patterns of results for image scanning and mental rotation tasks. So these are people that have never seen things directly in front of them. So it's a pretty interesting thought to think that they probably aren't using visual imagery, because if they haven't seen something before, how can they depict it in their mind in a way that it involves their sight? So it's just an interesting result of the study that they can do the same things that we can do when we're visually able to see them first and imagine them later. We also know that visual and spatial imagery have to differ from each other because in certain cases, whereas brain damage patients most of the time lose both their imagery and perception together, sometimes there's also cases of damage to one without the other. So where someone can do spatial imagery, but they can't do visual imagery anymore. So in one example, a patient named LH, he had brain damage from an auto accident. He was not able to name colors of common objects, but his mental scanning and mental rotation were still good, which shows that you can have one without the other. But what do sighted people use? The answer is both. We rely on I guess, what happens is people compensate. So if they lose their ability to do visual imagery, they're going to rely on their spatial imagery and vice versa. Whereas on most tasks, we use both. In some cases, it depends on the task. It depends on the person, on what exactly we do. You can also see that some people are better at using visual or spatial. It depends on the person. Some people are better at depicting vivid images and they have better visual imagery, and some people are better at turning objects and doing mental rotation. It really depends upon you and your unique brain. So some more backup for mental images not being pictures and being more like perceptions. Um, if you remember, Dr. Starling at one point talked about the Necker cube, which for some reason is at the top of my slide here and inside the with the word inside of it. So the Necker cube can be perceived in different ways. It's ambiguous. It can be understood as a depiction of a cube from above or a depiction of a cube viewed from below. So in other words, the picture doesn't specify in which way the cubes, in which way it should be perceived. The picture is neutral with regard to interpretation. And you can go with either interpretation that you want to figure out how to perceive the object. Unlike the picture, though, your perception of the cube is not neutral. It is not indeterminate with regard to depth, and at any moment in time you perceive the cube as having one arrangement in depth than other, your perception, in other words, goes beyond the information given. So essentially, the configuration of depth is in just one way that your perception goes beyond the information given in a stimulus. So you have different things you're going to identify in your percept that might be different than when you're actually perceiving the object visually. So generally speaking, when you have a mental image of an object, that mental image is more like a perception. It can't be neutral. You have to interpret the stimulus for what you're visualizing. So that's different from having the object directly in front of you. Another example of this is the duck-rabbit image that you've seen previously. So in another example, in Reesberg and Chambers, participants saw a sequence of 10 nonsense shapes. They were given 5 seconds to memorize each shape, and the last shape in the sequence looked like that. They were asked to rotate the remembered image 90 degrees clockwise and identify the geographic form. What is it? So remember, knowing what this image was and trying to identify it was very hard for people, and what we found was that it was very hard to rotate and flip and change images that were ambiguous, as opposed to images that we already have pictures for in our brain or memories for in our brain. So we do find that we have mental images stored in our brain, most likely in working memory, that we maybe pull from our long-term memory into working memory when we're asked to imagine something. Our mental images are more like pictures than descriptions in this way. We know that scanning an image takes time proportional to the distance scanned. We know that we can zoom in and out of images. And we found that we can rotate images in 2D and 3D based on all of the different studies that were discussed in this section of the lecture and in these slides. We also know that there is a degree of functional equivalence between imagery and perception, that when we are doing one or the other, the different parts of our brain involved are very similar and sensitive. And we've discovered that images are more like perceptions. They are not neutral. An image is an interpreted stimulus based on our previous knowledge. So it's impossible to really visualize a random nonsensical stimuli because we don't have a mental picture for it in our brain. And that is it for the visual imagery section of the slides. If you have any questions, please let me know. We'll go from there. I know that this was probably a little awkward because it's the first time you've had this lecture material presented in this way. I'm finding it's a little clunky for me to be doing it in this way, but hopefully you get something out of this. And if you need anything, please let me know. Thanks so much.